All right, ladies and gentlemen, class recording has started. So, Monday and Tuesday, we started talking about motion graphs. And for all day Tuesday all day yesterday and the last part of Monday, we were talking about position versus time graphs. So first, in a very obvious kind of way, position versus time graphs tell us two things. What do position versus time graphs tell us? Position and time, right? So they basically tell us where and when, right? Where and when. But we also talked about the idea that the position versus time graph can tell us the velocity as well. How do we find out the velocity on a position versus time graph?
Change x over time.
What part of the graph tells us the velocity, right? The slope will tell us the velocity, right? We kind of went through, and not that one, but we talked about rise over run, and that's meters over seconds, and et cetera, et cetera, et cetera, right? Here, yesterday we talked about different types of graphs related to constant velocity motion and accelerated motion. How does the graph differ when we go from a constant velocity motion to an accelerated motion? It curves, right? The accelerated motion graph is somehow, some way curved, but a constant velocity graph is going to be straight lines, right? They might be horizontal, they might be slanting up, they might be slanting down, but they're going to be straight. Whereas in accelerated motion, an object is curving, or the graph is curving. All right, real quick, to summarize this up, not that one, there it is. So yesterday at the end of class, we went through and we did this graph, yes? And we talked about how this graph basically represents when we throw something into the air and then catch it again, right? We talked about how the slope changes. First it starts off shallow at spot number 1, then it gets steeper at number 2, right? Indicating that the object is speeding up. That's like when we throw the ball into the air. But then from 2 to 3, it goes from being steep to being shallow. So that's what happens on the way up. It slows down, right? Then past A, it switches from a positive slope to a negative slope, right? Indicating that the direction changes. And from 4 to 5, it gets steeper, so it speeds up on the way down. And then again at 6, it gets shallow again, so we end up catching it. Okay? Good? All right. So today, we're going to talk about this graph. All right, so there's one big difference between this graph and the graphs we've been looking at over the past couple days. What's the difference? It's a speed and time graph, right? And so, again, just to be more consistent with our wording, come on. There we go. Let's make that a velocity versus time graph, okay? So, what's happening to the object that is being represented here in this graph? If you were watching this object, what would it be doing?
Speeding up.
Speeding up, right? What's continuously happening to the y value on this graph? It keeps going up and up and up and up, right? This is an object speeding up, right? Bonus question. It's not with any points, but it's a harder question, right? What is the acceleration of this object? Talk to the person next to you. What is the acceleration of this object? Go. Good, good. Talk to the person next to you. Do we have...
You said go and you looked at it, so it's the same
So. I like the way you said it.
There's a roller.
All right. So, Edie,
Yeah.
what's the acceleration of this object?
4 meters per second squared.
4 meters per second squared, or 4 meters per second, right? If we look, in order to calculate the acceleration of any object, any motion, we need to know two things. What two things do we need to know to calculate the acceleration? The change in velocity and the time, right? Change in velocity and the time over which that occurs. So according to this graph, how much does the velocity change? 16, right? It goes from 0 to 16 on the velocity axis. How much time goes by during that change? 4 seconds, right? So if it changes by 16 meters per second in 4 seconds, that's an acceleration of 4 meters per second per second. Good there? All right, so velocity versus time graphs. Velocity versus time graphs are graphs of the instantaneous velocity. Are we cool with that word instantaneous? Are we familiar with that word instantaneous? Okay. All right. Instantaneous, like it's kind of built into the word. Instantaneous means like at this particular moment in time. So at a particular spot in time. So right now, or now, or now, right?
Or now.
Or now. So, the instantaneous velocity of an object over a period of time. Meaning, what does this graph now tell us? Position time graphs tell us where and what. This graph where and when. This graph tells us we can tell acceleration from that graph, but if in a very like kind of obvious kind of, sorry, I should stop touching my fingers because I was using that for instantaneous and that's not what we're doing right now, right? In a very obvious kind of way, right? What does the velocity tell us? What question does velocity answer for us? Remember way back when we talked about the 4 questions?
Speed and direction.
Speed and direction, or if we go in a more general sense, it tells us what is an object doing, right? What's happening right now. So it can tell us how fast an object's going, but also which way that object is going. Position graphs tell us where and when. Velocity graphs tell us what and when. Good? But they can also tell us what next, right? We calculated from the slope of the graph, well, I guess, so, sorry, I kind of jumped there, right? Edie, when you and everybody else calculated the change in velocity over the time, right? Change in velocity occurs on which axis of this graph? The y-axis. Change in time occurs on x-axis. So the change in velocity is the rise, and the change in time is the run, right? So the acceleration, or we can tell the acceleration by figuring what about this graph? The slope, right? So on this graph, time is the x-axis, velocity is the y-axis, but if we calculate the slope, that will give us the acceleration of that object. All right? So in this picture right here, right? If we had to describe the motion of this object, what would we say is happening? Okay. Talk to the person next to you. Describe the motion of this object if you were watching it. Go.
Starts at 5 meters. Stays there for 10 seconds.
No, it stays at constant speed.
Yes. Speed is at last.
No. Speed is not.
Stays at
Speed
last.
is constant speed. That last one probably the.
Because it is there.
It's around 5 meters.
Listen to him. Listen to him on this one.
Going 5 meters. So
For 5 seconds.
why? 10 seconds. That slows down.
All right. So, if we were describing this motion, what would we see? For the first 10 seconds, what is this object doing? Moving at a constant velocity. And that constant velocity is 5 meters per second, right? What happens from 10 to 20 seconds? It goes slower, but does it change direction on this graph? What has to happen for an object to change directions on this graph? It has to go below the x-axis. Because what tells us the direction on velocity? Positive or negative? Velocities don't get negative until we get down here. Right? So from 10 seconds to 20 seconds, if we were looking at that object, right, its velocity goes from positive 5 to positive 4 to positive 3 to positive 2 to positive 1 to 0. It's doing what? Slowing down. Okay? Good there? Next question. What's the acceleration of the object as it's slowing down? Talk to the person next to you. Go. What's the acceleration of this object as it's slowing down?
What? Yeah. I'm smart. Yeah. Go to the bathroom.
Alright, so what tells us the acceleration on this graph? How do we calculate the acceleration on this graph? The change in velocity over time. And we said that if we calculate that from this graph, what feature of the graph is that? The slope, right? What's the slope of the yellow highlighted section? All right. What happens to the velocity during the yellow section? It slows down. It goes from what to what? 5 to 0, right? So the final velocity is 0 minus the initial velocity, which was what? 5. Positive 5, right? How much time goes by? 10 seconds. So what is the acceleration of this object? Negative 0.5. Okay? Does that make sense? Good. All right. This is a negative acceleration, right? Physically, what's happening to the object here? It's slowing down. Remember when we first introduced acceleration, we said acceleration doesn't always, or negative acceleration doesn't always mean slowing down. In this case, it will, because during this section here, what sign do all the velocities have? They're all positive velocities. They're getting smaller, but they're all still positive, right? But the acceleration we calculated as negative. So when we have a positive velocity but a negative acceleration, physically what happens to our object? It slows down. When they have different signs, right, it slows down. Okay? Good there? Okay? All right. Here, I'm going to do this because I forgot we were going to do this. Here are some markers and some colored pencils. The next graph that we're going to look at might be easier to, not might be, it's easier to interpret if we have some color on it, all right? So, let's start by doing this, okay? All right. Like we buy things from Drug Mart. We have an account with Drug Mart. All right. I'm going to start off by highlighting a couple sections of this graph so we can use it to describe what's happening. Okay? So the first section I'm going to highlight in pink. I'm going to highlight this section right here, this small little section, and then this section right through here. Okay? You don't necessarily have to highlight them the same color as me, just as long as you sort of pick my, right? So the next section I'm going to highlight. The next section I'm going to highlight is this section up on the top, highlighted in green. Okay? Then I'm going to highlight this section and that section, both in blue. And finally, I'm going to highlight this section and this section. Oh, no, let's not use that. Hold on. My bad. This section and this section in yellow. All right, so in the bottom left-hand, easy. In the bottom left-hand corner of your slide paper on the back page, there are six questions that relate to this graph. Okay? It may be easier to answer those questions instead of with times with colors. Okay? So, why don't we take about 3 minutes and talk to the person next to you and answer the 6 questions that are at the bottom of your slides there at the end of the packet. All right? So talk to the person next to you and let's go. Well, I mean, it's your notes, right? You know, so you're going to have a quiz on this, so it might be a good idea to write it down. Yeah, colors is fine. At this point, no.
First 40 seconds is not the rate. And then 20 seconds, it accelerates to 3 meters per second until the 125-second mark.
It's your notes. You're going to have a quiz on this on Friday. But to directly answer your question, do you have to write it down? No.
That's what I said. Like, why can't you still write that down? Dang. Well, my green is your approximately, no, we don't have approximately, we can't color. What is the other? So turn, it's when it goes into 275, but that's time, so at 275 seconds. Like, can we write that?
Sure. Yeah, I mean, technically that would be a right answer to that question, but it's sometimes hard just to see those numbers, and you know the colors work a little bit easier when we're describing this stuff.
what is that? What?
What would I put from 250 to 600?
Anything that is a straight line outside of the block.
That's not asking.
Everything what then?
Yeah, what kind of line is this? What kind of line is that?
Straight. All lines are straight.
Yeah, but what kind of line is that? It's not going this way. It's not on the x-axis.
Like some of y'all love my legs.
It's this. See, feel this right here.
Wait, that was 250, 600.
I have 500. You see that?
You really need this. All right, let's take 30 more seconds, then we'll discuss. 30 more seconds, then we'll discuss.
Does anybody else use this?
Well, I use it for a lab.
We do? What, the rolling object goal thing? The thing where we measured? Yeah, I did.
Flying through the air.
Did we do that one already?
No, we haven't done that.
Well, then add it now. It's in your room. It's called Joe blah blah.
You're not in a position yet to start naming things after
What?
this. 1 month into freshman year, you can't just like claim things, right? See this ball right here? This ball is like,
What, that awesome lacrosse ball?
yeah, that's like, it's got like seniors' names on it and stuff like that. People who graduated, you know. So,
Oh, I like that.
all right,
I'm gonna name this name.
if we go with that, like, maybe the Jolie ball.
The Jolie ball named after Matthew.
All right, so let's discuss. Okay, so velocity graphs, they are complicated. Okay, keep in mind that in order to tell us the velocity of something, the graph has to describe two things, right? In order to describe the velocity, we need to know what? Direction and magnitude. What do we call the magnitude of velocity? Speed, right? How fast and which way? All right? So, question. Not one of the 6 questions on your list. Just question relating to this picture. What is the fastest velocity that this object ever travels? Go ahead, Drew.
3 meters per second.
Go.
What?
5 meters per second.
Oh.
It just happens to be traveling which way when it's going 5 meters per second. Right? -5 is the fastest velocity on this entire graph. Just because it's down low doesn't mean it's not fast. Okay? On position graphs, any horizontal section we said represents what? On a position graph, if it's horizontal, it's at rest. Okay? But on this graph, where does it have to be in order to be at rest? Or was that what you were going to say, Jane? Anywhere on the x-axis, right? It has to be on the x-axis if it's going to be at rest. Okay? Good there? So, like I told the people as I was walking around, there's reasons why I colored different sections of the graph the same color. Okay? what does pink represent? At rest, right? Pink sections are when the object is at rest. Okay? What does green represent? Constant velocity. In this case, constant velocity in which direction? A positive, right? So I believe one of your questions was, what is the object traveling with a constant velocity in the negative direction?
Yeah.
Is that one of your questions?
Yeah.
Right?
It says backwards.
Backwards, so I would say backwards, right? When is it traveling backwards, right? What's the answer to that question? It's never traveling with a constant velocity backwards. If it was, right, what would that look like?
Line below the x-axis.
Horizontal line below the x-axis. We don't have any of those. Okay? Right? One of your questions, question number 2. Well, sorry, we answered when was the object at rest, right? Those are the pink sections on this graph. Question number 2, when is the object traveling with forward with a constant velocity? That's the green section. Okay? At least on my graph, yours might be a little different, but you know. Okay. All right. Here's where things get tricky. Okay? Let's talk about yellow. Okay? So, the first yellow section on my graph, the one to the far left, what's happening there? It's speeding up. It's speeding up in a positive direction. Okay? It goes from 0 to +1 to +2 to +3. That's getting faster. Right? What about the second yellow section?
Also getting faster.
It's also getting faster, but in the negative direction. That second yellow segment, the velocity goes from 0 to -1 to -2 to -3 to -4 to eventually -5. Something that's velocities that's going -1 to -2 to -3, -4 physically is doing what? If the velocity goes from -1 to -2 to -3, it's going faster, it's speeding up, right? So even though one yellow section points upward and one yellow section points downward, they're both speeding up. Okay? All right. This blue section that I have the highlighter on, right? What's happening there? It's slowing down, but it's still moving which way? Still moving positive or forward, right? The other blue section, right? The line is sloping upward. But if we were looking at that object, what would we see during that blue section? It's slowing down as well. It goes from -5 to -4 to -3. It doesn't make it -3 maybe, but, right? The values are getting smaller, even though the line is going upward. Yes? Does that make sense? Okay? So we have to make sure that we keep track of not only how fast something is going, but also which way it's going. Because depending on whether we're above the x-axis or below the x-axis, that means different things. Okay? Does that make sense? Do we have any other questions about the 6 that we need to discuss? About the 6 that you answered there? After our discussion now, hopefully you have them all. So. For number 6, what's happening between 500 and 600? Is that what the last question says? Right? Yeah, it's slowing down, but in a negative direction. Right? Elena, go ahead. Right, so what color transition basically would we look there? Yeah, well, here, does it turn around here? No. These are all negative, right? So which color transition are we looking at? Yellow from what? Pink, right? Yellow from pink. Here it was going blue. Here it's at rest. Now it's going the other direction, right? Yeah, so that transition from pink to yellow would be a change in direction because it went from positive to negative. Okay. What else? Any other questions that we need to go over? All right, tomorrow we will get into the lab that goes along with this unit and then quiz on Friday. Quiz on Friday.